All right, everybody, welcome back. We're going to continue along in our discussion about alpha carbon chemistry. We introduced enols and enolates again from Organic Chemistry 1. We talked about tautomerization between ketones and enols. And then we talked a little bit about the equilibrium properties of enols. We talked about the acidity of those alpha protons and how we can use them and take advantage of them to make enolates. We said that under acidic conditions, under acidic or basic catalytic conditions, we're going to get some enolate and we're going to have some of the original ketone starting material there. But we can irreversibly produce enolates as long as we can control the product. So we can, as long as we can get rid of one of the side products and have it leave the reaction like hydrogen gas, forcing the reaction to go to completion, or if we can use a really strong base that won't react with the alpha carbon or with the carbonyl carbon, excuse me, and force the reaction to completion that way. So now that we know how to do some of these reactions, let's start to take a look at some of these reactions. We'll build up to Aldol condensations, but then we'll stop there because we're going to have to then take an in-depth look at crossed aldol condensation, and that'll need its own video. So let's get started. All right. Okay, so we started off with talking about different conditions that we can use to do alpha carbon chemistry. Now, under acidic or basic catalytic conditions, we don't form enolate irreversibly, but there is some enolate present. So here's a reaction that you should know. This is called alpha halogenation. It's in acidic conditions in this case. And what it does is it adds a bromine here at the alpha position. Yields are okay. They're around 65% yield. You can use bromine. You could use iodine. You could use chlorine, but you can't use fluorine as usual. Okay. Let's take a look at the mechanism. So we're going to use H3O plus as a catalyst. And if we think about the mechanism that we've already looked at, we know that under acidic conditions, the first thing that's going to happen is that we're going to protonate the ketone. Okay. Once we've done that, now we can show a resonance structure where we've got some positive charge on the carbon. Now, at this point, water can come along and act as a base. And form an enolate. Okay. Okay. But remember that the enolate, or this is actually an enol. So remember that the major resonance contributor actually looks like this. And it would be more appropriate to show it as the enol form so that everything is nice and neutral. Now, the enol will go on and react with the bromine. And it will do that by coming out with the double bond and attacking the bromine. Now this gets my bromine attached. Now water can come along and do a final deprotonation to reform the ketone. And now I have an alpha halogenated ketone. All right. All right, so the first part of the mechanism involves the tautomerization. That's this part, up to here. And then the tautomerization uses the enol as a nucleophile, and that starts here. All right, so what would happen if we did this reaction with a substituted alpha position? And so I just want to talk a little bit about regioselectivity. So let's imagine starting here. In this case, there's two possible products. I can have the product where the Br attaches at that side, and I can have the product where the Br attaches on the other side. It turns out this one is the major product, and this one is the minor product, and the reason is it's about the intermediates. The intermediate enol for this one is more substituted than the intermediate enol for this one. And so just by virtue of it being more substituted, it's lower energy, and that way the reaction proceeds faster to this product. All right, we can use, now once we have a ketone, an alpha halogenated ketone, if we react it with a base, then we can eliminate the bromine, and we now have an alpha beta unsaturated ketone. The base can be pyridine, lithium carbonate, or potassium tertiary butoxide. So potassium tertiary butoxide, let's see, let's make this right. T-but, okay. Potassium tertiary butoxide is fairly strong. Pyridine and lithium carbonate, they're not necessarily that strong, but because of the conjugation that's formed here between the alpha beta position and the double bond to the oxygen, I don't need a particularly strong base to do that. And so what that does is that introduces a way to, in 2 steps, introduce alpha beta unsaturation, with the first step being the alpha halogenation and the second step being treatment with a base, the final product being the alpha beta unsaturated ketone. Okay, another reaction that we need to know is Hell Hell-Volhard-Zelinsky reaction. The mechanism is not well understood, so I won't attempt to talk about how the reaction takes place is from a mechanistic standpoint, but I will introduce the reaction because it does introduce a bromine in that alpha position to the carboxylic acid, and it does so in pretty decent yields. You could then eliminate that bromine and then do other synthesis with it. So there's a reaction that you have to know, and so I'm going to leave that kind of just up at the top there. I'm not going to talk about the mechanism of that because we don't know well the mechanism of that. But I want to go back to alpha halogenation, but I want to consider it instead of under acidic conditions, I want to consider it under basic conditions. Now, you still get in essence an alpha halogenated product with hydroxide directly deprotonating the alpha position to form an enolate intermediate, and then the enolate intermediate directly attacking the bromine to form this species. Now, it turns out that this species, the alpha halogenated ketone, is more reactive to basic halogenation. And so for every hydrogen that's there, you're going to get another halogen. So you really can't stop this polybromination from happening. Now, the reason why I bring this up is because this has an interesting consequence. Let's imagine doing this on a species like this. Just like before, this position doesn't have any, it has 3 alpha protons, and so that means I'll end up with three bromines there. And so it turns out that if I react this with base under these conditions, what ends up happening is that I end up replacing the CBr3 with an OH. In order to do that, hydroxide attacks the carbonyl carbon, forming a tetrahedral intermediate. And even though, we don't typically expel carbons, because of the electronegative nature of because of the electronegative nature of the bromines, the negative charge on the expelled carbon is stabilized. And so it actually does end up being a pretty good leaving group. And so while halogenation under basic conditions is not particularly useful for adding one halogen, it's better to do that under acidic conditions. We can use alpha halogenation as a two-step process with some acid workup to neutralize the CBr3 anion that's produced to actually remove a carbon and create a carboxylic acid in the process. So there's the reaction that you should know. I want to make sure that's the one that we're focusing on. Okay, so we're starting to move in a little bit further into this section, and now it's time to do another reaction that we're actually going to spend quite a bit of time on, and it's called an aldol reaction. And I'll show you what I mean by aldol. And the word is aldol, and hopefully you can start to see that that means aldehyde and alcohol. If I take an aldehyde and I react it with sodium hydroxide and water, then and this is why I'm excited, I form a carbon-carbon bond. Here was the previous alpha position, and now I have a new beta position. And so this is called a beta hydroxy aldehyde. And we can also have a beta hydroxy ketone. So here's the reaction. Let's take a look at how this works. So again, this is alpha carbon chemistry, and the conditions are basic. So the hydroxide is going to directly deprotonate the alpha position and form an enolate. And now maybe you see that in the presence of an enolate, it should be an excellent nucleophile that can attack a carbonyl carbon. And so that creates the carbon-carbon bond. And now there is a tetrahedral intermediate here with a negatively charged oxygen and a hydrogen. So what happens at this point now is that the negatively charged oxygen will reform the base from the water that was formed in the previous step. And that's where I get my beta hydroxy aldehyde. And I'm not showing the hydrogen in this case. Now, it really does depend on whether or not, or what the identity of the reactants are in order to predict the yield. Let me give you an example of this. If I react 1, 2, 3, 4 butaldehyde in this reaction, then I formed this product in relatively decent yields. But this is an equilibrium, and under other conditions, with other examples, like if I use hexanone, this is produced in relatively low yields. And so the reverse reaction is actually taking place. And so we do want to be able to get a feeling for what's going on in order to do a reverse aldol reaction. And so we start off on this side with our alpha, or with our beta hydroxy ketone in this case. And we see how the base can react with the beta hydroxy ketone and reform the two separate ketones. And so let's take this out of the way. Let's take this out of the way. Let's make it an OH. Now we can get our arrows going in a specific direction. Got a negatively charged oxygen there. And the negatively charged oxygen reforms its carbonyl group and expels the electrons in that carbon-carbon bond to reform a neutral ketone plus the enolate. And then the enolate can react with the water that was created and reform the other ketone. And since this is the same ketone, we're going to get the same cyclohexanone product. Okay, and so there's one other reaction that I want to talk about before we end up this video, and that's called an aldol condensation. So here we talked about how to make aldols, and now I want to talk about an aldol condensation. So if I take an aldol, so an alpha beta hydroxy, a beta hydroxy ketone, or a beta hydroxy aldehyde, and under acidic or basic catalytic conditions with some heat, then I can actually eliminate the OH group and form a double bond here. What's driving this reaction is that I'm forming a conjugated pi system here. So this gives me, and this is the reaction that you should know, a way to create an alpha beta unsaturated carbonyl group in one step. And so all I do is use the same reactants, but then I want to add some heat to it. Oops, and I need to redo this because that's the product. Starting off with an aldol and ending up with the unsaturated product. So the aldol addition Let me start this over. There we go. So starting with only the ketone, I can get to the alpha beta unsaturation. Now it does go through an intermediate beta hydroxy aldehyde, which then becomes dehydrated. So this is the Aldol Addition, and this is the Aldol Condensation. Let's take a look at the mechanism of this. So let's start off with just our ketone or our aldehyde, and let's react it under basic conditions. Recall that under basic conditions, the first step is to form this enolate with the hydroxide doing a proton transfer. And the enolate can then react with another one of the ketones by acting as a nucleophile. And that's what forms the carbon-carbon bond. I still end up with this negatively charged oxygen that ultimately gets reprotonated. And I form the aldol. Okay, here's the new part. Here's the next steps. Now, remember that I've got some protons here in the alpha position, and they are susceptible to being deprotonated by this hydroxide. And that will form yet another intermediate enolate ion. And because the conditions of the reaction are basic, I can expel this hydroxide. And since I'm forming a conjugated system, this reaction is thermodynamically favored. And this is the ultimate product. Okay. Of course, this one would be the major product, and the other possibility would be a cis alkene. This one is the minor product for the same reasons that we discussed before. Okay, and so what I want to do is I want to leave it there because this introduces the concept of aldol reactions. And up to this point, what I've done is I've shown you aldol reactions, but I've used the same starting material. And what we have to do is we have to get more interesting examples and use two different starting materials and see where that goes. So that'll require a little bit longer of a discussion. So I'll see you with that later.